So this last unit is mostly on differential equations. It's got some extra stuff in it, including this lesson, as well as the last lesson of the unit. But 2 of the 4 will be on solving differential equations. Today, we're going to talk about U substitution. A U substitution is a technique to find antiderivatives. Where you can't find the antiderivative normally. It is going to help undo the chain rule. Now let's recall the chain rule. If I'm taking the derivative of a composition of functions, we took the derivative of the outside, left the inside alone, and then multiplied by the derivative of the inside. So cosine of 2x, the derivative was negative sine 2x times 2. The derivative of root x cubed plus 1 would be the derivative of the root first, with our inner composition kind of inside staying there, times the derivative of the inside, right? Comfortable with that? Could do that as well here, but whatever. What we're going to be doing is we're going to be going backwards here. We're going to start with something that is a derivative of a composition. And we will take this and we will have to figure out how to turn this back into root x cubed plus 1. How we go from here, negative 2 sine 2x, and realize that its antiderivative is the cosine of 2x. Okay? There's a technique for us to use that will help us figure it out rather than just kind of, well, help us just do a step-by-step process to figure it out rather than just like looking and trying to figure it out, which we might be able to do. Now, we can already do one of these kind of techniques to help undo the chain rule without knowing, this whole U substitution process. If I asked you to take the antiderivative of cosine of 3x, I would hope that you guys could do that. Okay, go ahead and do that right now and see if you can figure it out. You know that the antiderivative of cosine is sine, and you know you're going to have that 3x. You know you're going to have some plus c. But is the antiderivative just sine of 3x? If I took the derivative of sine of 3x, would I get cosine of 3x? No. And of course, remember, if you're ever trying to check to see if your antiderivatives are correct, we could take the derivative of this, and if the derivative of this is that, then we're good, but the derivative of sine of 3x is cos 3x times 3. Right? Chain rule. Well, that is not the same as that. I need to somehow get rid of this 3. Well, what can I put maybe in front of sine of 3x so that I'd be able to get rid of that 3? Good. I threw in a 1/3 here. Well, then my derivative would be 1/3 cos 3x. The 1/3s and the 3's will go away, and this is correct. So we just kind of figured out, hey, I need that 1/3 right there. And you could kind of do this for anything, a antiderivative of a product, even something as simple as e to the 2x. Right? You should probably know that, the antiderivative of e to the x is e to the x. We'll probably need a 1/2 in front of it. We haven't specifically talked about the antiderivative of e to the x yet, but we'll talk about it today. Okay? We should be able to just kind of figure that out. All right? Well, let's say we couldn't figure it out, or we had something that is more difficult like this guy. Right? It's not obvious what to do here. It's not obvious what the antiderivative is. I don't even know where to start. We have something like this. I don't know where to start here. I don't know what to do here. Okay, I'm going to need a technique for these specific antiderivatives. They're very specific in nature. They have to be set up a certain way. You cannot use this technique for any function. It is only to undo the chain rule. Okay? So here it is. U substitution. It's also called the change of variables technique. Only for specific functions that are derivatives of something like f of g of x. Okay? Now, we're taking the antiderivative of f prime of g of x times g prime. This is the derivative of the chain rule. I know that my answer in the end is going to be f of g of x, right? So I know that if I'm trying to take the antiderivative of this, I'm going to end up with equals f of g of x plus c. But maybe we don't see that. Maybe it's not obvious. Here's our technique. We're going to start with a step 0, which leave blank, and we will come back to later. Step 1, the most important step, the step that you might have to try a few things out before figuring out that you've done it correctly, is you're going to pick u equals g of x. Now in this one it's obvious g of x is shown, but for another one that I will show you, might not be obvious, like if I have this guy here. I want to set u equal to g of x, but what do I select? Well, typically, the g of x is going to be the inside of a composition. Okay? Other times, you're just going to have to figure it out. So, here's g of x, and this one is just demonstration purposes. I set u equal to g of x. Step 2, I'm going to take the derivative of u equals g of x. Now, I'm going to show you a step that you will be skipping in the future. When you take the derivative of u equals g of x with respect to x, you get du dx equals g prime of x. Okay? This step right here, you're going to skip and you're going to go to the next piece, which is we are going to multiply both sides by dx. Why? Because I got a dx right here. And I'm actually going to replace that dx with something. So I'm going to multiply both sides by dx and have du equals g prime of x dx. So we're going to take the derivative, make it look like du equals g prime of x dx. Always. Okay, we want just du on the left side, and we want the right side to be the derivative of that inside times dx. I'm going to need that dx here. Okay, so I'm skipping this in the future, and I'm jumping right to du equals g prime of x dx. I'll show you that in a second. Okay. Next step, we will solve for dx. Okay. So I'm going to divide g prime of x. I'm going to write it as 1 over g prime of x times du. I like to do that to keep things separate, keep that du kind of off separate from the 1 over g prime of x. Okay. All right. Here is substitution, the substitution part. Move this over. We'll call this the U substitution part. That means we are going to substitute what we set u equal to, but we will also substitute what dx is equal to. I'll say sub 4u sub 4 dx. Or sub in u sub 4 dx is what I meant to say. Sub in u sub 4 dx. Okay? So what does that mean? That means when I have g of x, I said that was equal to u. I'm going to put a u there. And now here's the key. dx is right here. I'm going to take this entire thing that is equal to dx, and I will replace the dx there with it. Everything else stays. Okay? So this is what it's going to look like. Integral of f prime of u times g prime of x, which is this right here. Now instead of dx, I will have 1 over g prime of x times du. If you selected the correct u, you will see stuff cancel. And you will be able to take the antiderivative of this new function with just u's. So we're just going to leave u's after stuff cancels. Here, what will cancel? The g prime and this g prime will cancel, leaving me with just the antiderivative of f prime of u du. All of a sudden, I have just u's. Okay? We will then antiderive the easier integral. The antiderivative of f prime we'll say is just f. And the last step is to replace that u with g of x. Plug g of x back in for u. So u is equal to g of x. I have f of g of x plus c, the answer that I was looking for at the beginning. That's just how we got there. It's very involved. There's lots of steps that I wrote down. I typically don't like to say all these steps, but I feel like with this technique, it's important to just go one step at a time. Okay? Let me show you one that we were looking at, this one, where it's not obvious what we're going to do. And we will use this technique to find this antiderivative. Okay? Step one, set u equal to something, g of x, which is what we typically say is the inside of a composition. Okay, when we're talking about something that we can take the antiderivative of using this technique. Look at 3x root 9 minus x squared. What would we say is the inside of a composition in that? So the root 9 minus x squared is a composition. It's the root and the 9 minus x squared. Okay? It's an outside and an inside. We just want to pick the inside. So I just want to pick the 9 minus x squared. So everybody, we will write down next to this that u is equal to just the 9 minus x squared. The inside. Typically, that's for the easy ones, it's the inside. Sometimes it's not going to be so easy. Okay. Next step, we will take the derivative. Now, we usually have du dx is equal to negative 2x. Instead, we will write it as du equals negative 2x dx. Okay, so we're going to have to get used to writing a derivative just for this technique this way. Now, let's go ahead and solve for dx. That's the next step. Solve for dx. Write it as 1 over whatever you have times du. Keep the du and the other stuff separate will help. Everybody with me? Next, we will substitute in what u is equal to, and we will substitute in what dx is equal to. So dx is here. I'll replace that with that. U, this guy, u goes here. Go ahead and do that. We good so far? Now, I told you if you pick the correct u, stuff will cancel and you'll be left with an easier antiderivative to take. Will stuff cancel here? Yeah. This x and that x can cancel each other out because we just have multiplication. So all of a sudden, those x's go bye-bye, and I just have, after kind of rewriting it, negative 3/2 root u du, which I can take the antiderivative of. So I'm just taking the antiderivative of like the square root of x. I can take the antiderivative of the square root of x. Recall, this is just x to the 1/2. If I'm going to take the antiderivative of x to the 1/2, I use the power rule. Add 1, multiply by the reciprocal. I get 2/3 x to the 3/2 plus c. So here, the antiderivative of negative 3/2 root u will be u to the 3/2, and then 2/3 will be multiplied by this negative 3/2, which works out nicely, plus a c, giving me just negative u to the 3/2 plus c, which is my antiderivative, but topping it off would be to take what u is equal to and summing it back in at the end. Subbing it back in at the end. If you took the derivative of this, you would get this. This is a crazy way to go backwards in this case. Okay? Now, the same technique could be done for that previous example, the cosine of 3x. I'll just show you really quickly. We have a composition. I can set u equal to the inside of that composition. The derivative would be 3 dx. dx is equal to 1/3 du. I can sub in, I'll have cosine of u times 1/3 du. Well, I can take the antiderivative of cosine u, that'd be sine u times 1/3 plus c. Well, that's the same as 1/3 sine 3x. Now, would I expect you to use this entire technique for something that we can do by looking at it? No. If you need to do it, well then do it. But this is just showing you that U substitution undoes the chain rule here, and there's that 1/3 that we needed that we kind of just figured out at the beginning of class, but it just pops up if you're doing the correct procedure. But we need practice, so let's practice. Let's do this guy right here. Take the antiderivative of x squared times x cubed plus 3 squared. Let's make it cubed. That way we don't think of doing anything crazy. What will be easy to tell is whether or not we picked the right U, because if stuff doesn't cancel, you didn't pick the right U. If you end up with X's and U's, you didn't pick the right U. Try again. Or maybe we shouldn't be using U substitution at all. Maybe there's another thing that we should be doing. The X's do cancel here, which is great. I have 1/3 U cubed. This should be a du, Mr. Messner. Now, what a lot of people do is they miss this next step, and they simplify things, and then they stop here, and then they just plug u back in, and they say the antiderivative is 1/3 x cubed plus 3 cubed. No, we still have to take the antiderivative. Don't forget the very important step of actually taking the antiderivative. This would be u to the 4th times 1/12, 1/4 times 1/3 plus c. That is a crucial step, and now we can replace the u with x cubed plus 3. Okay? Good. Let's do another one. This one right here. Good? Seems easy, right? When it's obvious like this, when you have this composition, you got an inside of a composition, it works. It won't always be obvious. We'll need to be able to see that this is, a g, and this is a version of its derivative g prime. That's why we're canceling, because it's f of g of x times g prime of x. We're having g prime of x cancel when we take the derivative of g. Same thing here. This is the g, this is the g prime. When I run into something like this, we see a bunch of compositions, but one is going to be more helpful than the other. I can even make it let me put that square here. Okay. Now, of course, you can rewrite this as tangent x secant x squared, right? All of my instincts are telling me to select what as u. And all of your limited instincts are telling you to select what as u. Secant, right? All right, let's take secant and let's see what happens. substitute it in dx, I substitute it in u, and I get this. And I say, all right, well, this tangent cancels with that tangent, right? But what happens is I have u squared and I have 1 over secant x. I have x's and u's. I actually picked the wrong u, even though this screens pick secant. It's the inside of a composition. Mr. Mester told us to pick the inside of a composition. Well, I said typically the inside of a composition. It will not always be. We have to start kind of training ourselves to look at derivatives of pieces. I know that the derivative of tangent is what? Secant squared. If I thought this was g, I actually can write this as tangent to the first power, and there's my composition. What's the inside? It's tangent of something to the first power. Tough, but I know that the derivative of tangent is secant squared. I'm going to use that to my advantage. So go ahead and set u equal to tangent, and let's see what happens now. We get 1/2 tangent squared x plus c, because I'm ending up having to take the derivative of just u, which is just x. The antiderivative of x is 1/2 x squared. So that's how I got 1/2 u squared plus c, okay? So we get that. We have to be careful in the future of things like that. But let's look at these. And I won't go through the exercise of having you try to select u's and failing, because it'll take us some time and we got to move on. But I'll show you these as a great example of, hey, you learn this technique, you're going to think U substitution, U substitution, U substitution. Let's set U equal to t minus 2 over t. That makes sense. And then you'd find that not everything cancels. You're not helping yourself out. And then you're going to try, oh, set u equal to t squared. Let's try that. Well, you're not going to help yourself out there either. It's not going to work out. Turns out, how to take the antiderivative of this is to go back to the old distribution and to use the power rule. And that is going to lead you in the right direction. Same with this. You might think, oh, set u equal to maybe this root x or maybe this 4x squared. But turns out what you really should do is simplify. And this is root x plus 4x to the 3/2. And you could take the antiderivative of these. Okay. So what was step 0? Check to see if you can simplify first. Okay. Don't even use U substitution unless you're really sure this is what you need to do. Okay? Okay. Well, let's now find an area under a curve using U substitution. So I got an area between 0 and 2 of x root x squared plus 2. Now, we know that if we didn't have a calculator, we can approach this by taking the antiderivative and using the fundamental theorem of calculus and finding the change in the antiderivative. So we're going to have to take the antiderivative of x root x squared plus 2. I can do that. What should I set u equal to? The obvious answer is correct today for this one. Thank you. Goodness. I don't know why I'm surprised anymore. So I get u equals x squared plus 2. du is equal to 2x dx. dx is equal to 1 over 2x du. And I go ahead and replace things. So I have x root u 1 over 2x du. My x's will cancel. I'll take the antiderivative of that, and I get 1/2 times u, so this would be u to the 3/2 times 2/3, so that'd be 1/3 u to the 3/2 plus c, but we know we don't need the plus c, right, because we're going to find the change. Well, here's the problem. If I plugged in 0 and 2 here and 0 and 2 here, this would be wrong. Okay? Those numbers, as they are right there, are wrong. Now, if I went ahead and replaced that with x squared plus 2, which is my last step, then those numbers are back to being correct. When we change from x's to u's, our boundaries, which are x's, need to be changed to u's if we want to be correct all the way through. This is x from 0 to 2. This is x from 0 to 2, I have x's. If I switch to u's, I can't use x's. I need u's if I'm to be perfectly correct as I'm doing this. Now, how I'm going to take an x and turn it into a u? What should I use? I should use the situation I've already established, which is my connection between my x's and my u's, which is that u is equal to x squared plus 2. So actually, when x is 0, u would be equal to 2. And when x is 2, u equals 6. So this should be 6 and 2 and 6 and 2. And turns out, if you evaluated this here, it will be the exact same as this evaluated. It's just, where do you want to do the extra step? Do you want to plug g of x back in, or do you want to just evaluate this with 6? So this is equal to 1/3 6 to the 3/2 minus 1/3 2 to the 3/2. Or if I plug in 2, I have to square it and add 2. This ends up being 1/3 6 to the 3/2 minus 1/3 2 to the 3/2. You get the same answer. You can either do it with u's or you do it with x's. Now you might be thinking, well, Mr. Messner, I'm just going to do them with x's, so why do I need to know this? I'm just going to plug back this in and I'll just keep the x's and I have to change those x's to u's. Well, because you will have questions like this, where you have an integral and they will ask you on an AP test to write a new integral with just u's, and it's almost like fill in the blanks here. What goes here, what goes here, and what ends up being over here? Well, in this case, you're going to have to know how to change those x's into u's. Okay? Let's go ahead and try to tackle this problem. We know that we want f of u, so that means that u is going to be equal to 2x. We should do this. We will see this type of problem again. This would be the procedure to go about this. I would say u equal to 2x, du is equal to 2dx. That means dx is 1/2 du. So dx doesn't just turn into du, it turns into 1/2 du. It's very, very important that we see that. We substitute in u. We also change our x's into u's. That's an x. That's an x. These are now u's. Once we do that, we can take this 1/2 out. It's just a constant. Multiply both sides by 2 to get the integral from 8 to 18 of f of u du is equal to 12. And that would be the correct answer. Questions about that? We'll do another one just like that. I'm telling you, u is going to be equal to root x. What's the integral from 1 to 4 of e to the root x over root x? Understanding that the antiderivative of e to the x is just e to the x. Maybe you replace u both places. Who knows? However, we should know that u is equal to root x. So actually this and that will cancel. So you don't have x's and u's. You will just have u's. Okay, and you can actually find this. So the antiderivative of e to the u is e to the u. Between 1 and 2, you'd have e squared minus e. Done. But that wasn't the question. The question was to write it in terms of an integral with u's. Okay? So we need to be comfortable changing our variables when we use U substitution. Not because we'll have to do it. Like in this previous example up here, I do not have to change these into U's if I know I'm going to just end up with X's in the end. X, X, holding X's there. And maybe I just forget about the numbers until the end. We'll end up with the same answer, but there are specific questions where they will require you to change your X's into U's. Why is it e squared minus e? Because it was e to the second power minus e to the first power. I'm finding the change in the antiderivative. The antiderivative of e to the u is e to the u between 1 and 2. E squared minus e. Well, so again, good point. You could keep it as u's as long as you're using u's, or go back to x's. Sorry, we would have this be e to the root x, but this wouldn't be from 1 to 2 anymore. This would be from 1 to 4. Right? 1 to 4 are the x's, 1 to 2 are the u's. You end up with the same answer, e squared minus e. E squared minus e. They'll be the same after you plug them in. Okay? This 2. What happened to that 2? Thank you. Don't let 2's disappear on you either. Okay, now this leads us into the next one, which are antiderivatives of e. We know that the antiderivative of e, if the derivative of e is just going to be e to the power. We'll have to be a little bit careful, though, with U substitution. Okay, now this example right here is an example that I kind of showed you at the beginning that you can just figure out. You can figure out that when you take the derivative of e to the 3x plus 1, you're going to have that additional 3. You should be able to figure out that this antiderivative would be 1/3 e to the 3x plus 1 plus c. Okay? However, maybe we did not figure that out. So, if you have something where you don't have just e to the x, you will set u equal to the power in e. Why? That's the inside of a composition. It's e to the power. Well, we're taking u and set it equal to the inside of the composition. In this case, the inside of the composition would be the power. Now I'll show you how I can get the same answer using U substitution. U is equal to 3x plus 1. Du is equal to 3 dx. Dx is equal to, there's that 1/3 du. I'd have the antiderivative of e to the u times 1/3 du. The antiderivative of that would be 1/3 e to the u plus c, 1/3 e to the 3x plus 1 plus c. Okay? Well, you guys take the antiderivative of 5x e to the negative x squared. You're going to have to use U substitution. Ready, set, go. End up with negative 5 halves e to the negative x squared plus c is the antiderivative of 5x e to the 3x plus 1. Okay, the antiderivative of e to the x is e to the x. The antiderivative of e to the u is e to the u. If we see something a little bit more interesting than that, maybe we need to use U substitution and set u equal to the power, which is the inside of the composition. Okay. Same goes for these two. However, this one is a little unique. Let's write that one down. Antiderivative of 1 over e to the x dx. I would not set u equal to anything right now as I see it. Any ideas on what I should do? Instinctual reactions. That's the ticket. We should rewrite it as e to the negative x. And you should be able to figure out that this antiderivative is the same as its derivative. It's negative e to the negative x. If you can't figure out that it's negative e to the negative x, you can set u equal to that negative x to figure out that you need that negative 1 somewhere. Okay, this one, your instincts of setting u equal to 1 over x would be correct. You would just go from there. Your x squareds would be able to cancel. Things are great. Okay. We'll get the antiderivative of 5 to the x. Anybody remember what the derivative of 5 to the x was? Or 4 to the x, or 6 to the x, or 8 to the x, or pi to the x? What was the derivative of a number to the x power? Five to the x times the natural log of the number. if you remember that. So that's why with e to the x, we could actually do the same thing. It's e to the x log e, but log e is 1. Get rid of it. Derivative of e to the x to e to the x. What do you think the antiderivative of 5 to the x is then? I'll tell you, it's not just 5 to the x. What else do I need? Besides a plus c. I need something that will get rid of this log 5. I need 1 over log 5. Okay, which is something that you have to figure out. Throwing that in there just because I saw it once on an AP test. Just once. Okay? The derivative of 5 to the x is 5 to the x log 5. The antiderivative, you got to count for that log 5. Just like the derivative cosine of 3x is negative sine 3x times 3. Well, if I'm taking the antiderivative of cos 3x, I'm going to need to be able to account for that 3, which is why I need the 1/3. All right. Now let's talk about log and its antiderivative. Well, not really the log of the antiderivative of log, not the antiderivative of log. The antiderivative is something else. Before we talk about it, let's talk about the power rule problems with the antiderivative of x to the negative first. I want you guys to all, using the power rule, take this antiderivative. Show me what you get. Knowing that x to the negative first is the same as 1 over x. Also take the antiderivative of 1 over x squared, which is really just the same as x to the negative second, right? We can just rewrite that and use the power rule. Let me first start by doing x to the negative second. All right, we add 1, we multiply by the reciprocal. So the antiderivative of 1 over x squared is negative 1 over x. Okay, cool. Now let's look at 1 over x. What is the antiderivative of 1 over x? Well, if I use the power rule, I add 1. Negative 1 plus 1 is 0, right? And then I'm multiplying by the reciprocal. So am I multiplying by 1 over 0? This seems a little funky, right? Because the power rule does not work for x to the negative first power. Your antiderivative is not 1 over 0 times x to the 0. It's not correct. Okay? The way we kind of remember what its antiderivative is we recall the derivative of the natural log function. What was the derivative of the natural log of x? 1 over x. If it was f of x, it'd be 1 over f of x times f prime of x. Well, guess what the antiderivative of 1 over x is? The natural log function plus a c. Seems so easy, and it kind of is, but also it kind of isn't. There's a problem here. The problem is that log is only right here. It's only for x is equal to, x is greater than 0. So when I tell you what is the derivative of log, you say it's 1 over x, but it's actually just 1 over x for those values. 1 over x looking like this. Okay. So yes, this is true. The antiderivative of 1 over x is log x. But just for x is greater than 0, if I just look at the natural log of x. Log, it does not exist to the left of 0. So I can't say this is true for all x's. Okay? But if I'm talking about the antiderivative of 1 over x, I am talking about the entire function 1 over x, which is defined to the left of 0. So if I ask you this question, what is this, for all x's except for 0, I need to be able to adjust my answer here. Because I need some function whose derivative, who gives me the slopes of the tangents to that. Okay? And what ends up happening is that we need to take this log function and also flip it this way. And what this graph is y equals the log of the absolute of x. And turns out the derivative of log absolute x is 1 over x, but for all x's, except for 0, because you can't have the log of 0 or 1 over 0. And it turns out if I just ask you this, without talking about any specific x values, you must tell me that its antiderivative is log absolute x. So I need an absolute value if I'm taking the antiderivative of 1 over x, and there's no distinction of the domain being positive x values. Okay? If we go this way and I just start with x, log of x, well then I can answer 1 over x because I'm automatically constraining my domain to positive x's. But if I go the other way, I'm going to have to really expand that logarithmic function. Okay? Now, we will see with logs like this one, if I have 3 over 5x, a lot of people instinctually, they write this as 3/5 x to the negative first, and then they try to use the power rule, and the power rule won't work. Okay? X to the negative first, you can't use the power rule. We have to instead leave this as 3/5 times 1 over x. And remember that the antiderivative of 1 over x is log absolute x. So this antiderivative is 3/5 log absolute x. This guy, we need a step 0, but do not write this as x to the negative first because the power rule won't work for that. Instead, use the power rule for the x, use log absolute x for x to the negative first. Okay? But there is also going to be U substitution with these. We will have to see that sometimes, if I see that this is a derivative of that, I will set U equal to my denominator. And watch what happens. I'm going to keep going after the bell rings. If you want to stick around, you're more than welcome to, but I got to finish the video. And you guys can leave and just watch the end of the video if you choose to. So I have x, I have u, I replace dx with 1 over 2x du. All of a sudden, I just have 1 over u times 1/2. Again, the antiderivative of 1 over would just be log absolute u. And finish off by plugging in the x squared plus 1. So you need to be aware, if you see this, U substitution, you'd set u equal to the denominator. It actually is the composition. This is something to the first power. For these two, you can see that we have a coefficient in front of the x. Now I'll show you, using U substitution here, that we're going to need a 1/4 in front of things. Be 1 over u. This is 1/4 du. The antiderivative would be 1/4 log absolute u plus c, or 1/4 log absolute 4x minus 1 plus c. Now again, in the future, you will not have to do something as involved as this. You'll be able to figure out, since this is just x to the first power, we have a coefficient in front of it, we'll be able to just multiply by the reciprocal of the coefficient log absolute whatever is in the denominator. And that is the correct antiderivative. Couple more, and that's it. This guy, our instincts would be correct if we set the u equal to the denominator and went from there. Du would just be equal to e to the x dx. dx is 1 over e to the x du. So it's e to the x over u times 1 over e to the x du. Cancels. We'd have log absolute u plus c. Then we would see this. We'd set u equal to tangent because the derivative of tangent is secant squared. I'll finish off with these two. All right, so this one's a tricky one because we have 1 over x log x. We end up setting u equal to the entire denominator, it won't work. In this one, we kind of know that the derivative of log would be 1 over x, and actually that's how we're going to be able to eliminate some things. I get 1 over x u times x du. The x's will cancel. The antiderivative would be log of u, log absolute u. And then I would go ahead and just rewrite this as log of the log of x between e and e squared. Now you can either go between log of u, and it's actually easiest if you replace these x's with u's using this. So if we have e squared, u would be 2. If we have e, u would be 1. So between 1 and 2, we end up with log of 2 minus log of 1, which is just log of 2. If you wanted to go back to x's, you could. The log of the log of x between e and e squared. But again, you would just get log 2 minus log 1 over log 2. Finally, tangent. We can finally do tangent knowing the antiderivatives of log. If I rewrite tangent as sine over cosine, watch what happens. I know that sine is a version of the derivative of cosine, so I'm going to set u equal to that denominator because we have g prime up here in g. I get du is equal to negative sine x dx. dx is equal to 1 over negative sine x du. This becomes sine x over u times negative 1 over sine x du. Sine x's will cancel. This becomes negative log absolute u cosine of x plus c. This is the antiderivative of tangent. Something a lot more complicated than we probably thought it would be. Negative log cosine of x. And finally, remember, you're going to think that whenever you have a x to a power in any denominator, you're going to think its antiderivative is log. It is not. If you say that this antiderivative is the log of x squared, you are wrong. Don't make this mistake. Instead, rewrite it as x to the negative second and use the power rule. All right.